Hi everyone, this is Nicole Granucci and this is my Physics 100 lecture on acoustics. In this lecture what I want to do is actually talk first a little bit about what waves can do. Now we talked about some wave properties, but I'm going to specify some wave properties that occur when objects interact with each other. So I'm going to talk about a wave property called reflection, refraction, and diffraction. But more importantly, talk about what is called acoustics, how the sound waves interact with the environment. So we'll talk about how geometry affects these materials, and time permitting, for Physics 100, you'll do a lab kind of investigating some of these properties as well. So the ultimate big idea for this is how do sound waves interact with the environment? So we can make a sound, we learned about what sound is all about, what it can do, how it travels, interacts through interference. But what happens when it hits a wall, or a barrier, or a window, or some other sort of medium? So we're going to look at that and investigate that today. So like I said, my goals is to talk particularly about reflection, refraction, and diffraction. Now these are properties of waves. So that means that even though I'm talking about it very specifically to sound, these apply to light waves and any sort of form of waves, so water waves as well. In fact, if you take a physics course, like a pretty, standard physics course, you'll actually go through each of these as separate classes. I usually spend a lot of time teaching reflection and refraction and diffraction as separate lectures, with light specifically. With reflection, we talk about mirrors, refraction is lenses, and diffraction, we usually talk about coherent light waves. But today I'm going to talk specifically about sound for physics of sound. And like I said, talk about the acoustics. So, like I said, these are some wave properties. You might have heard these before, but this is what waves can do with a medium. In other words, what happens when the sound wave hits something. So, the thing that we're going to spend the most time on is called reflecting. So I think you kind of know that already, just through your personal, intuition and experience. But that's when something bounces off another surface. So we're going to talk a lot about that, because sound waves can do that. Sound waves can actually transmit, which means it goes through the substance without, bending or, any really physical changes. It just goes right through the substance. Put a little asterisk there because I'm not going to focus on that, although that can literally be an entire class itself. Waves can refract, meaning it passes through a medium with a bending of light. And I'll talk about what I mean by bending of light and how this occurs, because it is a special case. But super important, especially with light, because that's how lenses work or glasses work. And then, of course, I'll relate that to sound waves. How do sound waves bend? And then lastly, we'll talk about diffraction and how waves can actually bend around corners and what that can imply. Okay. So, first I'm going to talk about reflection of waves. As you might imagine, reflection is when a wave hits the surface and comes right back. That's the basis of it. Of course, there's some complications with that, but let's just talk about the simple cases. So, first of all, if I took a slinky, of course I know this is completely, if I was in class, I would do a visual of this just to give you an idea, but I'm sure you can, picture this in your mind, but you'll see that I have a slinky and I send a wave down. If I have somebody holding the slinky or a wall, this is attached to a wall, but it could be someone holding the the other end of the slinky. The wave bounces back. That's reflection. But when we talk about reflections of sound waves specifically, they're called echoes. So if you ever done that canyon thing where you're like, echo, and you hear echo, that's because the sound wave went forward, hit a surface, and then came back. So that's what this diagram is right here. I don't know if I can make myself a little smaller. I like talking to you when I have these videos. But you can see the same idea, just different way of displaying the same information. So the red lines represent the sound wave coming in, hits the object. The dotted lines represent the wave reflecting back. In fact, that's how sonar works. If you ever heard of that word sonar or radar, you send a sound wave out, it hits something, it comes back. We know the speed of sound pretty accurately, at least how fast it travels in air, so we can get distance and speed measurements from it. But as you know, this is an echo. So, in real life, things don't necessarily undergo total reflection. So total reflection is assuming that the wave that you get comes back exactly the same amplitude. That's total reflection. So if you notice the top little diagram up here, you'll see that a wave comes in, hits a surface. This is technically a free end surface, so that the wave stays on the same side. We're not going to talk about inversions, just what happens to the wave. More importantly, if you notice the amplitude of the wave or the height of the wave, they're the same in and out. This is total reflection. What does total reflection mean to sound? If you had an echo and it came back the same volume. That's very rare, because you usually lose energy to the absorption in the wall and the air itself and a lot of other factors. So total reflection is very rare, but in some cases you can do it. If you're pretty close to a wall and you have a nice reflecting surface, you can have this happen. But in most cases we have what is called partial reflection. So partial reflection is the reflected wave comes back but loses some energy. So I use this animation as a kind of a visual of what I mean. So if you know the incident wave or the incoming wave here in the less dense medium, notice the height of the amplitude, right? But let's pretend that this boundary right here is a wall, okay? So what happens is that when this wave hits the wall, not only does it invert, which I'm not really going to talk about, but more importantly, notice that the wave that comes back is not as high as what it started with. Notice it's smaller, right? This is higher and this is smaller. That's partial reflection. So it comes back softer. So this is generally the case of sound waves. Sound waves hit a wall, they come back, and they're definitely a lot softer. So what you're seeing beyond here, actually, which is something, like I said, I'm not talking about specifically, is transmission. So notice the wave keeps going. So yes, you can hit a wall, and some of that energy related to the amplitude can go into the wall. So more dense medium. So less dense can be the air, and more dense can be a wall. This can be many applications. This is generalizing some cases here, but this can go from air to water, or you can do something like glass to diamond, because diamond's more dense than glass. So that's why this is a generalization. But I think you get the idea. Partial reflection is only a part of it comes back. But when it relates to sound, just to be repetitive, we're talking about lower volume. This is majority of what echoes sound like. You hear it as echo, 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 right? They get weaker and weaker as they go. So that's a partial reflection. And yes, remember, energy is related to the amplitude of the wave. So like I kind of talked about earlier, where does the energy go? It has to go somewhere. It can't just disappear. Like I said, it can get absorbed into the wall, or it could get transmitted through the wall. So in other words, what can happen is if you don't hear an echo, there's a possibility that all the sound gets into the wall. And if it's completely absorbed, it means that it gets into the wall and gives energy to the wall by moving the particles, and that's it. It's gone. Well, gone, I'll put like that. But the point being is if you were to stand on the other side of the wall, you wouldn't be able to hear it. That's because the wall totally absorbs the sound wave. Or it can get transmitted through the wall. Like I said, usually because there's some reflection, you're not going to get a full transmission. Unless it's, the window's open or wall's open. But you can partially hear somebody, so that's transmission. So, if you're in a hotel room, or you're in a, trying to think of an example, an apartment that has, very thin walls, they say, you can hear someone's conversation. That's when your transmission occurs, and that's why your echo, if you have any, is much weaker because it went through the wall. So, regardless of the type of wave, all waves follow this thing called the law of reflection. So, whether you're sound, whether you're light, whether you're water waves. And all basically, the basic idea of the law of reflection, as complicated as it looks down here, is that the way the wave comes in is the same as the wave going out when it hits the surface. That's the law of reflection. So, using a very simple case, if the wave comes in straight, the wave goes out straight. That's essentially what that means. But what happens is if we start angling the light, or the sound, it just means that the angle is going to be the same. So if you come in at a 30-degree angle toward this vertical line called the normal, you're going to go out 30 degrees. I think it said 30, but in 30, out 30. That's all the law of reflection means. Kind of think of a mirror, if you notice the mirror here. If you took a light rays and you took like a flashlight and you angled it at 30 degrees, it will come out at 30 degrees. You're going to verify this in lab, whether it's a physical lab or digital lab, but you'll see that the law of reflection will actually adhere to pretty much any surface. And this is just an information slide, so I'm just going to skip this over. It's basically what I just said. You know, these slides kind of represent your textbook. But there's different ways that light can bounce off a surface depending on the smoothness of your surface. So you have diffuse and specular reflection. So I'm going to talk about specular first, which is B. Specular reflection is when every light that comes into the mirror is perfectly reflected at the exact same angle. What does that do? It gives you a perfect mirror image. In other words, mirrors are specular reflections. So everything else, if it's not a mirror or a super shiny surface, becomes a diffuse. So, for example, this is a piece of paper. So despite the fact that it's, paper, one of the biggest things, or most surfaces, is they're not perfectly smooth and flat like mirrors are. So if you notice, they try to exaggerate the roughness of paper. Even a smooth piece of paper has some rough characteristics of it. But what that does is that the light that comes in will bounce off at different angles because there's different hills and valleys that the light can bounce off of. Strangely enough, it does follow the law of reflection. So if it's at this angle, it's going to follow the law of reflection. But because the paper or a desk surface or the floor or the bed or, for example, the walls, most surfaces are diffuse. They send the light rays in different ways. Now, there's some cases where, you can see everyday objects that's not in a mirror. One of my favorite examples is a still lake. That's a specular reflection when you see the mountains and the mountains in the lake. So that would be like a specular reflection. Oh, I don't have any visuals of that. That's okay. I thought I did. And then a diffuse reflection would be that lake on a windy day. All the waves start to move. You don't see the reflection of the nice mountains on that day. So that would be just another example with light instead of sound. A little later, I'll talk about diffuse reflection and the importance of that with sound. But let's talk about another special sound reflection. So we talked about a single reflection, calling it an echo. You might have heard this word before. If you haven't, here it is. This is a new word called reverberation. Reverberation refers to multiple reflections. Usually this happens because you're in a small area and the sound waves, as you can see in my visual right here, can bounce on several different walls and several different areas. So basically a reverberation is just an echo multiplied by several times. So that's, an echo is just one bounce off, reverberation several bouncing offs. So this is just an example of a reverberation visually of what it can do. So I like this animation because it just shows you a quick difference between echo and reverberation. Echoes usually occur when you have a long distance to cover, right? Like a canyon wall. So you can see that guy gets really excited because he says, woo, and it takes time for that sound wave to go down and come back. That's an echo. But reverberation is if you say, woo, and you hear, woo, 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 woo. More, actually, you won't, you can hear that, but actually, I like to think of this as like a small room, like a shower or a really highly reflective room. So like a stairwell or something. You sound echoey. That sound kind of fills you up and it's kind of there because it lingers around. So if you notice this sound wave, this little three dots right here, or lines, they stay with you. So the sound kind of stays longer. That's the effect of reverberation. In fact, I think you need to hear what reverberation is. to kind of hear it. So I have an audio example. So this is just a YouTube video of that. So let me just grab it here. Have it already set up. We're going to watch it together. Just going to send this back a little bit.
I've come through now to the anechoic chamber. Anechoic means non-echoing. The walls, the ceiling, and even the floor in this chamber are lined with foam wedges which absorb the sound. So the room's almost free from reflections. When I'm speaking, all you're hearing is the direct sound from my mouth. You can hear the sound is much clearer than in the reverberation chamber next door, but correspondingly the overall sound level is much less.
Okay, so let me just pause this before it starts again. Okay, so I wanted to see what a reverberation sounded like, but I hope you noticed that it was actually kind of hard to hear him, right? Like, when I first watched this, I was like trying to pay attention to what he was saying because it was really hard. So reverberation's good because the sound is there and it's full. We lose clarity because of it. So that's one big downfall of having reverberation. And even though I didn't really talk about it yet, I will. The anechoic chamber, the one where you don't have any echo, if you notice the difference in clarity, right? You just have one wave coming from his mouth, really, to the microphone, to what you were hearing with that. We're going to look at another anechoic chamber a little later. That's reverberation. So reverberation's super helpful. First of all, the sound's more full. Like I said, it fills up the room. Feels like the sound wave is all over instead of in one spot. Some places where this happens a lot, you can even think about it, with some of your personal experiences, but, an empty hall. Now, I say an empty hall as opposed to a full hall because there's nothing to absorb those sound waves, like carpet or clothes or other people or other things. So the bigger and emptier it is, the less likely it is to absorb and more likely it is to reflect. So empty rooms really, I put a hall, but empty rooms are kind of some good examples. Or like a church, generally churches, when there's not many people in there, can have this effect. So small rooms really enhance this. So that's why you sound so good in the shower, if you ever wondered, if you sang in the shower. Because that room is, generally, of course there's exceptions to every rules, but, generally your shower is made out of tile, or if you have, like, those sliding glass doors, you're having a little reverberation chamber. So you have lots of sound that reflects many times, and you have a fuller effect. You sound better in a shower. So funny story, because I'm full of stories, is one time my wood floors were getting done. And, of course, you had to empty out the entire room for your floors to get done. Obviously you can't have anything there. But what you leave behind is this beautiful empty room. And I remember the first time I went in there and I was like getting that reverb effect. I was like, oh my gosh, this, reverberation effect. This is really cool. So what did I do? I got out my violin and started playing in there because it sounded so good. And I sounded way better than I actually do, which is exciting. Or my trumpet. I didn't bring my trumpet. I brought my violin that day. But I always remember that effect of reverberation. I didn't know it at the time, but now that I know what it is, I can definitely connect to it. So, you know, the small rooms really enhance this effect. So rooms smaller than 17 meters, so multiply by that by 3, so roughly like 60 feet, less than 60 feet, and that's a super, you know, over exaggeration of that. Highway tunnel, you notice if you ever, it's very echoey and loud, right? Because it's usually hard surfaces and, you know, lots of reflections happening there. So a common misconception, a lot of people think it's resonance that makes your shower sound better. Resonance relies on matching frequencies. This is not matching frequencies. This is about many echoes happening at once. That's what this effect is. So common misconception is reverberation that makes your shower sound better, not resonance. So we kind of talked about this already, but just to lay it out here, pros and cons, right? So pros is you get that fuller, longer sound. It sounds really good. And it overcomes this problem called the bass problem, which I'm going to explain next. And then the other, so cons is garbled sound. You lose clarity. So if you have too much reverberation, like, welcome to this is the day. Oh my goodness, you can already see how that can be really tough to listen to. And you have articulation loss. So if you have too much reverberation, it's not good. And not enough reverberation, you lose low frequencies. You lose the low ends. So it becomes a balancing act. What's the perfect reverberation time to keep things full but not too full? Excuse me. So I just want to just highlight this problem first, and then I'll move on here. But the problem is that when you have, just like bass notes in general, what happens is that bass is hard to hear. In fact, I'm going to use this slide first, even though it's next. I know this looks really complicated. You're like, oh, there's so many lines here and all that fun stuff. But most importantly, I just want to show that, you know, what we have here is the intensity. So loudness, right? And then this is frequency. So what this graph really tells you is that in order to hear something in terms of high frequency, and you want it to be low, it has to be really loud. So let's see. So notice that this is like 30 hertz. I mean, this is like, you can't really hear this really well, actually, but that's okay. Let's pretend. So this is a very low note. This is almost beyond the threshold of hearing for humans. But in order to hear this 30 hertz object, you have to have the intensity of at least 60 decibels, which is like an air conditioning loud. And then you need, in order to hear something really loud at that intensity, you need to have, well, again, you just need to be really loud. But the problem is loudness dissipates the further you get. So let me just connect those two again, just to be clear. This is saying things that are low frequencies have to be loud. Well, loudness is affected by how close you are. If you're right up here, the bass is going to be super loud, but if you put yourself over here at the end, the bass is going to be soft because the inverse square law. As sound, the distance from the source increases, the sound level or sound loudness decreases. And it actually fades faster in bass notes because we have a hard time hearing bass notes. We have to have a bigger amplification of that. So how do we fix that bass problem? Well, what we do, I'll just use this visual, is this, right? So yes, the distance will get, you know, the further away you are, the harder it is to hear it. But if I can make that same sound and bounce it off, the distance is a little shorter. Not by much, but it helps that bass problem kind of, kind of help it out. So multiple reflections help the bass problem. So turns out that there's this sweet spot for reverberation times. So how long the sound stays in the air, really. That's what a reverberation time is. So how long your echoes last. So it turns out that this red box here, you need longer times Notice that 2.2 is longer than 1.7, 1.4, etc. for the low notes to really be heard. And then vice versa. This is the reverberation times for higher frequencies. They don't need to be as long, but notice they're long. And notice I'm saying the word long as if they're like 20 seconds longer. They're not. They're just a couple of second, tenth of a second faster. Longer here. But having longer reverberation times really helps project low bass sounds. So, like I said, there is this sweet spot for clarity and reverberation time. Turns out that 1.5, 2.5 seconds is the sweet spot. And that means how long does the sound wave stay. So 1 second is a long time in orders of sound waves. So after 1 second it goes away. Usually this is generally for speech and music. So 3 seconds, if you think about it, if you count to 3, it doesn't seem like a long time, but if you think about it, if you count to 3, 1, 2, 3, that's how long the sound stays. That's kind of a long time. And then just to go to the extreme, think about it. For 8 seconds, 1, 2, 3, 4, 5, 6, 7, 8, right? Like, I know that was a little dramatic for a full 8 seconds there, but that's a long time, so that's going to have super garbledness. It's good for music where you don't really need too much clarity and blending, so like pipe organs. Like if you're just holding chords and just like playing, a nice set of, chords without any, melody, then that's totally fine. So like Notre Dame, that's a place where this happens. 5.5 is really hard to understand. So if that organ were to play like a nice like melody, you wouldn't be able to hear the difference between the notes. So that's too muddy. And then 3.3 starts to get, it's better, but organists like it, but not really good for speech again. So you can kind of, the melody gets kind of mushed up together instead of being really clear. So that's like the major difference here. Just going to shut off my sound. There we go. Okay, great. And then vice versa, going the other way on this chart here. Absorbing the surfaces shortens the reverberation time, so you get clearer speech. But then you start getting this thing called dead sound. So it sounds really like, if you've ever been in a quiet room, or if you've got your ears tested, or if you've been in a closed room with carpet, you get that like dead sound, like very strangely, silent. That's when you have no echoes, right? So you give just a pure, especially if you have no echoes, no reverberation time, gives a pure inverse square law of behavior. That just means that, the further you go, the weaker the sound is going to be. So that's a really big way of saying that. So here's some big name places that really focus on enhancing the reverberation time in the sweet spot so that it sounds really good. So some big places. I've been to Boston Symphony. That's really exciting. Of course, not before I taught this, but so I have to go back someday. But they kind of had these sweet spots, which is perfect for clarity for sound. And of course, all these places, if you aren't familiar with them, are big music symphony places where orchestras play, or other people other than symphonies play at Carnegie Hall. But that's really what they're designed to do. So this is their reverberation time versus frequency. So meaning that at the lower frequencies, they have longer reverberation times, and then at the higher frequencies, you have lower. Exactly what we expected. We need this to be higher to keep those bass notes, and they're designed for this. So let's talk about reverberation material. So what makes better reverberation versus not? So to enhance reverberation, you really need to eliminate things that absorb. So things that will reflect perfectly, as you might think or know, is hard objects, right? Concrete, ceramic, polished wood. Anything hard and metal, all these things, I didn't mention that here, can reflect these sound waves. What can diminish reverberation? Well, anything that absorbs. So it's the opposite, right? So things that absorbs are called acoustic tiles. They're actually all over Southern. If you've never noticed them before, because I never did until I started teaching, there are these big blocks of fabric on the wall, and they look like decoration, but really it's absorbing sound. Depending on the lab room we use, you can actually see them. Actually, there was a restaurant, a local restaurant that was having severe reverberation issues. So big and open and so much wood that all the sound get garbled. So it was actually really loud in that restaurant because of that. So they had to put up acoustic tiles. So what they did is actually, they were pretty clever. They actually, instead of making these big black blocks, because that's not as trendy, I guess, they printed like nice pictures on these acoustic blocks, but they're really made out of foam to absorb some of that sound. So anything with that's fabric-y usually is the case. Fiberglass, curtains, rugs, tile, things that don't reflect, things that can absorb the sound. Excuse me, I put windows in here as perfect absorbers. It just means that if you open up the window, the sound leaves the room. So that's one easy way to get rid of sound if you don't want a reverberation. But, of course, we're looking at ways to keep the sound in, but just, absorb it instead of get rid of it. In fact, if you want to absorb certain parts of the sound wave, you can do that. Called treble and bass absorbers. Treble means high, so if you want to take out the highs and you want to emphasize the bass notes, you want to select objects that have tiny holes, rough surfaces, so that the waves get caught and trapped in here. So sound waves that are high-pitched like this will get trapped in small areas and won't come out, because the sound wave, higher frequencies mean smaller waves. So you need small holes for small waves. And then, as you might imagine, we have bass absorbers, which is kind of the opposite. You need big spaces for those waves to get trapped. So egg crates, right? Large grooves, anything. You'll see in the anechoic chamber video, I'm going to show you how they remove those sound waves like that. So another story. So when I first bought one of my first houses I bought, of course we have to have a drum set and a whole band set up for my house, because that's a big hobby of mine and my husband's, and that's what we want to do. So we set up our whole band setup in the basement. And of course, the basement's full of hard walls, right? So we needed to actually absorb some of that sound. So we actually put a giant, literally just went to Bed Bath and just bought a few egg crates like this and put it behind his drums. So we'd actually absorb a lot of his sound, because he's loud. Drums are just loud in general. I think you've known that. But, when you're standing right next to him point blank, it's really hard. But also, the walls of the basement are perfect, reflectors, So the sound was not only loud, but in our face, all over, no matter where we stood. So a way we were able to fix that was to put up these egg crates. And you might notice that, or this kind of technique in sound, soundproofing rooms or recording studios and places like that to absorb some sound. So I'm going to show you this video. I love this video because it was actually a psychological video. What this talks about is, can you handle silence? So we have a person that's going to volunteer to sit in the silence room. Let's see how long he could, stay there, and I'll let them kind of talk about that. And then what I'm going to do after that is actually stop the video and then start the new section. This way I could break the video in half and do refraction and diffraction on a separate video. So this way you can break it up like that. But let's watch this first, since it's all related. I have it already set up for you. Oh, I'm actually going to take a quick step back, and we're going to listen to, this is called Flight of the Bumblebee. This is in a church. So you're going to hear the reverberation effect, the fullness of it. You just barely get articulate, melodies in here, but they do get a little garbled due to the room. But you can hear the fullness of the sound. This is a great band if you haven't heard of them. You can hear it. So you know he's playing a lot of notes there, and you can almost hear him distinctly, but it's kind of hard. But the sound's really full, so it sounds great. And if you're wondering, this is a very hard song to play, so it's really impressive that they do it so well. And notice that you hear mostly highs, right? It's really hard to hear the lows, and I know that's partially due to my speakers. But that tuba is really hard to hear. I just really like this song. We don't need to listen to the whole thing. You can listen to it, the link is there. Okay, this is what I do want you to listen to. So it's a quick 10-minute video, worth watching the whole thing. So I'm going to do this. Actually, they suggest this in the video too. I suggest that if you have headphones, especially really good ones, to put them on for this video, because you actually do hear things a lot differently. I was actually surprised when they told me that. I was like, nah, it's fine. I listened to it on my computer, and then one day I was like, fine, I'll go listen to it, and it was actually a totally different experience. So, you know, this might be a good place to pause the video, and I would suggest you do that. And why don't you go ahead and do that, and we're going to watch this together with the headphones if you have them. I'm not going to do that obviously here, but it does make a difference. So here we go.
As loud as I can, and I'm going to keep screaming as loud as I can while I spin around. I'll keep going until my breath runs out. Alright. You ready?
Yeah.
Okay.
I should have warned you about that.
That was outstanding. Thank you.
Thank you.
The quietest place on Earth is apparently an anechoic chamber in Minneapolis. Now, I'm here at BYU at their anechoic chamber. Anechoic is Latin. It basically means no echo. And the way they achieve no echo is through all of these foam wedges, which are put on the walls and even the floor. You can see that I'm actually on a spring floor, and down below me there are all of these wedges. Now, you may want to use headphones while you're listening to this video, because that's going to be quite important.
Low frequency sound will come in, and by the shape of it, bounce and just keep bouncing pretty much forever until it just gets lost in the wall.
So it's good
and then high
bass
frequencies
absorber.
are more so going to get absorbed into the foam itself.
You can hear how the room deadens echoes by clapping constantly while closing the doors.
If you look at the wave becomes flatter, which means there's less echoes. See?
Totally changed the quality of the sound. Definitely. There are reports that it's impossible to stay in one of these rooms and remain sane for a significant period of time. The record is apparently 45 minutes.
I felt a little claustrophobic. It felt like there was a lot of pressure on my head.
But why would that be? I mean, the air is no different in here.
What I figured is just because when you listen in a normal room, there's a lot of reverb. To your ear, that means there's a lot of space, but there's none of that in here, so it feels claustrophobic.
It feels like you're in a tiny room, like you could be in a coffin.
Okay, maybe, yeah.
Well, I think it's really an anxiety response. So you're used to having these sounds around you, and then you don't anymore, and so you start to panic because you don't have something you're used to. And I think that anxiety can increase and cause some stress, and maybe that's why people go crazy or hallucinate with sound. It's just because they're trying to make up for what they're used to that isn't there.
When I bring people in, I warn them, hey, if you get a little dizzy, please let me know so I can get you out of the room before you make a mess in our expensive facilities.
First, you'll hear any rustle of your clothing. So you move an inch and you'll hear it. Then you'll hear any fluids that are in your mouth or your throat. You'll hear them all moving around every time you move your mouth. And the longer you stay in there, the more you hear. So you start to hear the blood flow through your brain.
Have you heard it?
Mm-hmm. It sounds kind of like a ringing or a pulsing.
Can you kind of make the sound for us so that we know what to listen out for?
Of the blood flow?
Yeah,
it just sounds like a pulsing, like... Some people say they can hear their heartbeat coming from their chest as well.
Have you heard that?
No.
A violinist placed in one of these rooms was apparently banging on the door within a matter of seconds trying to get out. Now other people say it's impossible to stand up because you become so disoriented, dizzy, nauseous, and some people even hear oral hallucinations. But to me it doesn't sound right. You know, I believe that I should be able to sit in a room with no sound, with the lights off for as long as I like. And so I'm going to put myself to the test by staying in this room for as long as I can.
Have fun in silence.
Thank you. Now it is just me in the anechoic chamber. And this is probably the quietest place I have ever been. And in a second, I'll tell the guys, shut the lights off. Okay, I think... Oh, I'm ready. And the lights are off. I'm going to turn off the camera so I don't have this light. And then there's only the audio recorder that I'll keep with me. Not sure how long I've been in here, but I still feel quite comfortable. It's nice and quiet. I mean, that's an understatement. But it's relaxing. If I hear anything, I feel like I hear a low-pitched hum.
You can hear it better with the headphones.
If I had to guess about how long I've been in here, I'd say about 8 minutes. I feel like I'm more aware of my heart. I can feel each pulse, and I can almost feel it radiating up my chest towards my head, like a wave. In my ears, there's a hiss. I think that's just hearing loss. This just reminds me of that Mission Impossible movie where Tom Cruise sneaks into that building and he has to keep his decibel level low. Small sounds seem amplified. It's like your brain has recalibrated, so the quiet things seem much louder. I feel like I can feel more things, like with every beat of my heart, it feels like my body shakes a little bit. Like a device that has a little motor inside it, it gets shook around like a phone. Okay, Cameron, looks to me like we're good for time. If it looks the same to you, like we're around 46 minutes or over, I'm happy to hop out. So, yeah, when you're ready, you can flip the lights back on if you like. Are you there? Hello. I think I've been here for nearly an hour, according to my time checks, and I didn't fall asleep. I just, I've had a good time. It's a nice, quiet space. I kind of feel like this would be a good material to pad your bedroom in. Not a problem. Anechoic chamber, 45 minutes, an hour. Easy. I could stay in here for 5 hours. I think I could get a lot of work done in here. So, now I just have to get out. And I'm gonna see if I can exit this room without them turning the lights on. understand how anyone could go crazy in there. I mean, quiet is kind of nice. But then again, there are people who find all sorts of situations really uncomfortable, like just being in a pitch black room or being in a small confined space. So maybe those types of people would find this kind of unnerving. I definitely noticed that there were a lot of noises. Like, it wasn't just pure silence. Like, I actually had to work hard to make things feel silent. Otherwise, there was the sound of, like, just me rubbing my beard, or just, like, the rustle of your clothes, or every time you swallow, when you breathe. Perhaps the weirdest thing I noticed was, like, my sense of my heart. I just felt like it was pumping really hard, and I could feel almost like the blood pushing up through me. It wasn't like I was hearing it, it was just like I was feeling it. And I was feeling as though, in a way, my heart was shaking my body. That was something weird. But besides that, nothing crazy. No weird hallucinations or anything like that. So, I think the myth that you can't stay in here for longer than 45 minutes is busted. Even though this is not Mythbusters, I still think it's not true.
Okay.
Now, if you really hate silence, you should always carry an audiobook around.
Okay. So, anyway, thanks for, hanging out for that. So, I really like this, like I said, kind of like a psychoacoustic experiment, think about it yourself. Can you handle this room? Can you handle complete silence? What would you notice? Me personally, I think I would just be distracted. I think just like he was talking about, I think I'd like the quiet, but then I'd be distracted by all the things that I could hear. So I don't think I could get a lot done in this room. Excuse me, despite his ideas here. So, some of the challenges in acoustic design, as you can see, is trying to make sure you get an even balance of highs and lows, intensity, clarity, and little echo effects. So I'm actually going to stop this video stop the video at this point. In the next video, I'll talk about how we can overcome some of these challenges via geometry. Yes, geometry. Don't worry, we're not going to go into too much detail, but I'm going to talk about how the shape of a room can actually affect the echoes. And then I'll talk a little bit about reflection and reverberation. I'll talk a little bit about refraction and diffraction and what that does to sound waves.